Hello and welcome. This video today is all about transformers, and we're going to look at how transformers can be used for the national grid and also how they might be used for appliances around the house. But before we begin, we need to look at a couple of basic ideas behind how they work. So firstly, here I've got a magnet. This is a permanent magnet. We've got the north pole on this side and the south on this side, and what we can do is we can get a piece of wire and we can run it through the magnetic field. So the magnetic field runs from north to south, as we know, in this direction. But we could take a piece of wire and cut it through this magnetic field, and what would happen is we would cause a current to flow. So how would that work? Here's our piece of wire. Is connected to what we have here is an ammeter, so it's connected to an ammeter, and this ammeter measures current, and when we move the wire upwards, current will flow in one direction as measured by this arrow, and when we move it downwards, the current would move in the opposite direction as measured by the arrow. So we would have arrow going one way for one direction of movement of the wire, and then another way for another direction of the movement of the wire. If the wire is not moving, this arrow wouldn't measure any current at all. Now this is the actual basic idea behind producing electricity. This is how electricity is produced in our power station. Obviously it's not just a single wire being moved through a small magnetic field like this, but this is the basic idea behind it. But we don't often talk about, or we don't always talk about the current being produced. We often talk in terms of voltage or potential difference. And voltage and potential difference are both measured in volts, and you can use either term. The specification tends to use potential difference more often, but voltage is correct as well. But we talk about a voltage being induced over here rather than a current being produced. So another way in which we could actually cause that to happen would be to have a coil of wire, and instead of an ammeter connected here, I've got a voltmeter, and that voltmeter will measure voltage or potential difference in volts. And the way this works is we take the magnet, and rather than moving the wire, we have a coil of wire, we move the magnet, a permanent magnet, in and out of this coil of wire. So if we're moving in, we're inducing a potential difference in one direction. If we're moving out, the potential difference is induced in a different direction, in the opposite direction. So if we have, for example, if we have the permanent magnet moving in, the reading will go to one side on the scale. So here we have a 0, and we have a positive reading on this side and a negative reading on that side. So with the magnet moving in, we have potential difference in one direction. If the magnet is not moving, that's a bit untidy. If the magnet is not moving, we have no potential difference, and you guessed it, if the magnet is moving out, the potential difference is recorded in the opposite direction. So moving this magnet in and out of the coil can cause a potential difference to be induced across the wire over here. And this is the basic idea behind the working of a transformer. Remember, the job of a transformer is to either step up voltages or step down voltages, and we're going to have a look at how that works now. So before we begin, we've got a little simple device here. We've got an iron core in the shape of a C, and we've got a wire that's wrapped around the iron core, and we have a current flowing through that wire. Now, as you know from a previous video, if we have a current flowing through a coil of wire, we have produced an electromagnet. So here we have a magnetic field that is being produced. What we can do is we can introduce a similar sort of shaped device on the other side. This time it actually has more coils, but what we could do is we could actually hold this C-shaped coil of wire, and we could flip it up and down, and that means this electromagnet that is produced over here, we could actually physically flip it up and down, and that would make that electromagnetic field move upwards and downwards, or actually change direction, and that would cause the induction of a potential difference over this side. It's just the same as if we were moving a magnet from on this side up and down, and that would cause a current to flow, but importantly a potential difference to be induced on this side. Now it would actually be quite silly for someone to have to stand here and flip it with their hand, so we don't actually do that. We don't have someone flipping this C-shaped iron core. What we actually have is the current that changes direction by itself, and we call that alternating current, or abbreviated to AC. Alternating current changes direction by itself, so that means the electromagnetic field is also going to keep changing direction, and you should be able to use this idea to explain how transformers work. So if we were to try and put that into words, it might go a little something like this. So we have insulated wires that carry an alternating current in the primary coil. So we have here our primary coil, and I'll label all this for you in a minute so you can see it. But we have insulated wires carrying an alternating current in the primary coil. If these wires weren't insulated, the current would just flow directly from here straight through rather than going around the coil. We don't want that to happen, so the wires are insulated. Second sentence here is this produces a changing magnetic field in the iron core, so the magnetic field is constantly changing. This produces the magnetic field in the secondary coil. This is called our secondary coil, and this induces or generates an alternating, which means changing, potential difference or voltage across the secondary coil. So we can use potential difference or voltage there. And the final thing is, and so an alternating current is produced in the secondary coil. Okay, so this is a good way to probably describe how these things work. If you are lucky enough to get a 6-mark question on this, this would be a very good framework for you to use in order to respond to how these things work. Now here I have the similar diagram again. We don't need the gap in between that I had in the previous diagram, but this is the basic labels for our transformer. So we have our primary coil on this side. This is the iron core. The iron core is often made in layers of iron, or we call it laminated, which helps the functioning of the transformer. But we have the primary coil, and on this side we have the secondary coil. The alternating current is on the side of the primary coil, and this, as we know, helps to induce our potential difference on the other side. Now there's two types of transformers that we often talk about. There is one called a step-up transformer and one called a step-down transformer. This one here is a step-up transformer, and as you can see, there are more coils in the secondary coil than there are in the primary coil, so we know this is a step-up transformer. And the step-down transformer, as you can imagine, is the other way around. So this is the step-down transformer, and this has more coils in the primary coil than in the secondary coil. And one common place in which we see these things are in the national grid. So here we have a small version of part of the national grid. Here's our power station, and we have a step-up transformer. Just as the electricity is leaving the power station, the step-up transformer has a job of increasing the voltage as it's passed around the country, and our step-down transformer will be at the other end, where it needs to be stepped down so that it can be used. It can be a suitable value that can be used in homes and factories and so on. Now the next thing we have to be able to do is to do a couple of calculations based around this idea of our transformer and stepping up and stepping down voltage, and for that we need an equation. So here is our equation. Remember, these are given to you in the exam. You'll be told what the meaning of each one of these is, but you won't be given the units. So let's have a quick look at what all these mean. So for the first part of the equation here we have Vp, so this is the potential difference in the primary coil. So here's our primary coil, and we have alternating potential difference here, remember. And the second one here is the voltage or the potential difference in the secondary coil, and that is the same as the number of coils in the primary divided by the number of coils in the secondary coil. Okay, so if we have this equation, we can work out a missing value that we might have based on some information they give us. So let's have a go at a question. Okay, so here we have a transformer that has 500 turns on its primary coil and 2,500 turns on its secondary coil. The potential difference across the primary coil is 50 volts. Calculate the potential difference across the secondary coil. Okay, so this doesn't actually relate to this diagram. It's something separate that we're going to have a look at now. So if you want to, have a go at this yourself now. And then I'll go through the answers, but if not, I'll just go through the answer now and you can see how it's done. So all we do is we plug in the values into our formula. So what is it we are trying to find out? Which is the potential difference across the secondary coil. So this is what we're trying to find out. So we can plug in the rest of the information. So we have 50 volts in across the primary coil, so it's 50 over something we don't know, equals the number of turns in the primary coil, so it says 500 over 2500, so then that is simplified to 50 equals 50 over Vs equals 0.2, and if you're good at maths, which you do need to be a little bit in order to do these sums, you can rearrange, so we will have this here, so we have Vs is 50 over 0.2, and the answer then is 250, and it's the voltage or the potential difference across the secondary coil, so it's 250 volts. So we can see we've gone from 50 volts up to 250 volts. This is a step-up transformer. Let's have a look at one more example. You can again try this one for yourself if you want to. If not, the answer is I'm going to go through the answer now. So the input to the transformer is 230 volts AC from the main supply, and the output is 10 volts AC. There are 4,600 turns in the primary coil. Calculate the number of turns on the transformer's secondary coil. So again, we use the equation that we are given and plug in the information that we know. So we have 230 in the input side, so that's our voltage in the across the primary coil. That's divided by 10, and that will give us the number of turns on the primary coil, which is here, it's 4,600, divided by the number of turns in the secondary, which we don't know. So again, doing our maths, this becomes 23 equals 4,600 over our number of turns in the secondary, and if we rearrange, we have 4,600 divided by 23 equals 200 turns. So we have 200 turns on the transformer's secondary coil. Okay, so that's a quick run through of how transformers work and how to use this equation here. In the next video, which will be the last video for this topic, we're just going to look at the power across the transformer, and we're going to look at something called switch mode transformers. But for today's video, for now, that's me done. Thank you for watching, and I'll see you again soon.